Hello guys and girls, I am RajKrSingh and you are watching my video as a series of lectures on quantum mechanics. Today we will discuss on Wkb approximation. This is second lecture in this series of Wkb approximation. In the first lecture we have dealt and discussed upon the theoretical foundation of this approximation with its historical background, and we have discussed all the three cases of allowed regions, the forbidden regions, and the calculation of bond energy levels. In the second part of this lecture, we will discuss upon the validity condition of Wkb approximation. We will see under what condition this approximation is valid. But before going into details of this validity of the approximation, let us recapitulate what we have seen in the previous lecture. Those who have not gone through my previous lecture, which is the part 1 of this series, you are all requested to first go through that lecture and then continue with this video to have a seamless understanding of the flow of concept in this approximation. So we have seen in the previous lecture as this Wkb method allows to obtain approximate solution to time independent Schrodinger equation in one dimension. And this also helps in calculating tunneling rates through potential barriers and the bond state energies. And we have seen that this particular approximation is applicable to the system with slowly varying potentials. That is, in the system where potential is not constant but varies with some parameter associated with the quantum mechanical problem. However, the variation is not unlimited. There is certain restriction on the variation. We assume that potential remains constant over a region of the order of de Broglie wavelength. Therefore, Wkb method is also known as semi-classical case. Now, if Vr is not constant but varies slowly over many de Broglie wavelength, then solution for the wavelength is rapid oscillations modulated by gradual change in amplitude and wavelength. However, if potential Vr is constant and energy E of the particle is less than V, then the particle wave function has the form psi r equal to a exponential plus minus p dash dot r by h cross, where this p dash is imaginary and is equal to square root of 2m Vr minus E. That means the wave function in this case is also sinusoidal, but both amplitude and wavelength change with r. Now in the special case, when the potential is equal to the incident energy, then Vr is not slowly varying with lambda. Rather, this lambda equals to 2pi by p becomes infinite as the denominator, that is the momentum, becomes 0. When E equals to Vr, this bracket term becomes 0. So these points at which momentum vanishes and the wavelength becomes infinite are called classical turning points, because at this particular point particle stops momentarily and then returns back to resume the motion in the opposite direction. That's why they are called the turning points. Now, there are two reasons. One is the allowed region, where energy is greater than Vx, and in the forbidden region we have E less than Vx. The first allowed region, E greater than Vx, so E minus Vx is positive, and P square S x equal to h cross square k square with kx greater than 0. The general solution is the superposition of the two basic solutions representing the propagation of waves in two opposite directions. This we have seen in the part 1 of the lecture. And in the forbidden region, again we have the similar type of solution, except that in the exponential we don't have I, and the momentum p is imaginary in this case. Now in this lecture we will talk about the validity of this approximation. So from equation 8 we have this expression as equation 8 in the first previous lecture. Now here one of the first order term in h cross must be smaller than the zeroth order term. So if we take this assumption, then what we have, this term S0 dash S1 dash with this H cross, this must be much smaller than this term S0 dash whole square. So S1 S0 dash cancel out from here, and we have H cross S1 dash much less than S0 dash, and since this is equal to P, on the right side we have P, and S1 dash is P dash by P. These things are mentioned in the previous lecture. So from here, when we move on to the next slide, we see it is H cross d by dx of 1 by P much less than 1. So d by dx of H cross by P much less than 1. And this H by P is lambda, so it is H cross, so it is lambda by 2 pi, that is lambda bar. And this is equal to H cross by root over 2m e minus Vx. That is, equation 17 is the condition of validity of Wkb approximation, which says that the rate of change of de Broglie wavelength be small. That is, wavelength of the particle must change slightly over distances up to this order of size. That means it cannot randomly change to a very large value. But again, this condition of validity breaks down at the turning point where Vx equal to E and Px becomes 0. Classically, particle stops at this point and makes a turn for the motion along opposite direction. Thus, Wkb approximation is valid in both the allowed and forbidden region, but not at the classical turning points. अब हम लोग 3 different केस कंसिडर करेंगे. पहला केस होगा potential well with no rigid wall. The second case is potential well with 1 rigid wall, and the third case is potential well with 2 rigid wall. यहाँ rigid wall का मतलब पोटेंशियल के किसी पर्टिकुलर पॉइंट पर इनफाइनाइट हाई वैल्यू एज्यूम करने से है. So when we say that bond states for potential well with no rigid wall, then we have this type of potential, which is in the next slide. We have plotted here Vx against E, and we have divided it into 3 regions, 1, 2 and 3. In this region 1, you can see ये जो Vx है वो इस energy से ज़्यादा है. So energy is less than Vx, and in region 3 also energy is less than Vx. So this is the forbidden region. और ये जो बीच का रीजन है जिसको रीजन 2 बोल रहे हैं, इस रीजन में आप देखिएगा ये जो Vx है ये E से कम है. That means E is greater than Vx. So this is classically allowed regions. और ये जो 2 पॉइंट है x1 और x2, इस पॉइंट पर E और V इक्वल है. So ये जो 2 पॉइंट x1 और x2 है, these are the classical turning points. So we have written here very specifically, classically forbidden region is x less than x1 and x greater than x2 on the other side, and the classically allowed region is the intermediate region, x greater than x1 but less than x2, and x1 x2 are the turning points. So WKB method is applicable everywhere in the region 1, 2 and 3 except classical turning points. So the wave function must decay in region 1 and 2, which are the forbidden regions, and must be oscillatory in the region 2, which is the allowed region. Hence, from the basic and the general solution of the wave function, psi 1x expression हो गया first region में, this is C by P mod Px, exponential minus 1 by h cross, and this integral. Psi 2 यहाँ पे 2 term है within the region x1 and x2, or left going term and the right going terms, and in the third region we have the only 1 term that is going to the right side direction. So the quantized energy levels of the bond state is given by the closed integral px dx, that is equal to 2 times integral px dx from x1 to x2, and this is equal to n plus half h, where n can take values from 0, 1, 2, 3 and so on. इस इक्वेशन को ध्यान से देखिए तो आप पाइएगा कि ये इक्वेशन बोर्ड-सोमरफेल्ड क्वांटाइजेशन रूल को मैच करता है. ये जो क्लोज इंटीग्रल px dx है, ये पोजीशन और मोमेंटम फेज स्पेस में क्लोज्ड ट्रैजेक्टरी का जो एरिया इनक्लोज्ड होगा उसको इंडिकेट करता है. तो इन अदर वर्ड वी कैन से दैट ओनली दोज लेवल्स with energy En is allowed for which area of the contour P function of x and En given by this root over 2m En minus Vx this must be equal to n plus half h, where n is equal to 0, 1, 2, 3. So this was about without any boundary. Now we'll consider one particular case when the bond states for potential well with one rigid wall. So this is the shape of the potential, and these are the 2 points, classical turning points x1 and x2. At x2 and beyond x2, potential is more than the kinetic energy, and before x2 and within x1 and x2, kinetic energy is more than the potential value. So we have Vx equals to plus infinity for x less than x1, and Vx equal to some function of Vx for x greater than x1. x1, x2 are the classical turning points, and classically allowed regions are in the intermediate region between point x1 and x2. So again, the wave function must decay in the forbidden region, and it must be oscillatory in the allowed region. So psi x equals to a by root over px sine 1 by h, and this integral plus alpha. This alpha is the phase change factor within the 2 points x1 and x2, and the quantization rule for the bound state energy levels for the given potential with one rigid wall is given by x1 to x2 integral px dx, that is equal to n plus 1 by 2 plus 1 by 4, that is 3 by 4 pi h cross, and this n equal to 0, 1, 2, 3 and so on. So the only difference with the previous case is that here we have n plus 3 by 4, and in the earlier case we had, when there was no wall, it was n plus half only. Now we will consider the bound states for potential wells with two rigid wall. यहाँ picture में देख सकते हैं point x1 और x2 पर wall है, where the potentials takes the infinite values beyond which, and in between ये Vx का प्लॉट है, जो कि ये वेरिएशन, ये जो कर्वेचर है, this shows the variation of V with respect to x, and this is the kinetic energy of the incident particle. So we have explained the things here, Vx, and to remind you once again, the wave function has an oscillatory form in this allowed region, and x1 and x2 being the classical turning points. So in the next slide, we have expression for wave function in the region x greater than x1 just at the boundary x1. This is psi x equal to a by root over px sine 1 by h cross and so on. And for the region x less than x2 just at that boundary x2, we have this expression for psi x. And the quantization rule is again from x1 to x2 px dx, that is equal to n pi h cross. This time only we have n pi h cross. So this completes our discussion on the condition of validity of Wkb approximation and its application to 3 different cases of potentials. In one case it was having no walls, and in the other 2 cases it has 2 walls and 1 wall respectively. So this way we complete this discussion on the lecture on the second and the final part of Wkb approximation theoretical development. Now in the next 2 lectures we will discuss upon the applications of Wkb approximation. We'll take up the case of bound system, particle in a box in 1 dimension, and especially in the final lecture we'll take up the case of tunneling effect, especially linked with the alpha decay in the nucleus. Thank you so much for watching this video. Thanks a lot.